Okay. So what we're going to do, as Matt said, we're going to have a look at nonlinear analysis this week. Last week we did linear statics of our bracket. So this week we're going to take it a little bit further into nonlinear and hopefully explain where you get the differences between what you assumed last week in the linear analysis and what happens if you might have to use a different solver because you've exceeded certain limits of the analysis type that you chose last time. So that's what we're going to go through. Again, I've got my a slide in to explain who I am. I think most of the names that I saw on the list were the ones who were on last week, so we'll just skip past that. But I'm an FE analyst, used the tools for a lot of years. I've used Siemens tools for years, and I can remember. So hopefully I'll be able to help you through some of the analysis that you might want to do. So now we're going to have a look at nonlinear. So what is it? What is a nonlinear solution? It's something where your linear assumptions are not valid, which sort of maybe makes sense as a wording. But what we're trying to understand, well, what is that? Well, it might be material is nonlinear rather than linear. So last week we did linear statics. So if I apply a load of 10 and I got a deflection of 1 mil, if I just multiplied the load by 10, then my deflection would automatically be 10 millimeters. It wouldn't take into account the behavior of the material in terms of its stress strain curve. It would just be a purely linear Young's modulus. So that's one of the limitations. If you find you're close to yield, then you might want to consider material nonlinearities. The same thing would happen if you had geometry nonlinear. So what that might mean is my material hasn't exceeded its yield, but as I bend or as I apply my load, my structure deforms and then the load changes direction. So quite a common explanation for that is if you have your plastic ruler on the end of your bench, you put a force on the end. If you push it hard enough, you'll bend it all the way around where the force is no longer vertical. It'll maybe could even be at 90 degrees to the original applied load. So you want the load to change direction as you go through the simulation. And when you take your finger off the end of your ruler, then the ruler goes back to its normal position. So it's not plastically deformed. It's not gone nonlinear. It's just had a geometry nonlinear effect that you're taking into account. Contact can also be classed as a nonlinear situation where it goes to iterate on the contacts. You might have frictional effects. You might have other effects that you want to take into account as part of the contact. And hopefully, we'll go through and explain how these things come together. And as you might imagine, if you use the wrong assumptions, then you might get the wrong answer. So if you do a linear static analysis and assume that to be correct, it might not be because you might have used some invalid assumption. So hopefully today I'll explain how we introduce these nonlinearities and how we can start and assess what happens to the structures. So the agenda, very similar to what we did last week. We'll have a little bit of an overview of what nonlinear is. We'll go into the problem and look at that again and describe it. Then we'll go through the nonlinear process, looking at geometry nonlinear and then material nonlinear, and then we'll actually run the two of them combined. So we'll run geometry and material nonlinearities at the same time. So in terms of nonlinear solvers, Siemens and NX Nastran has a few different options here. In a basic license, which everybody will have, if everybody can solve Nastran like you did last week, then you will have access to Sol 106129, which is a Nastran nonlinear solver. So everybody can do nonlinear, even with a basic license. There are some limitations to that, which I'll introduce as we go through. We also have a multi-step nonlinear, which is a separate dedicated nonlinear solver. And this consumes tokens within the token licensing. I'm not sure, is everybody aware of what token licensing is?
Yeah.
Yeah. it means obviously you can take tokens, and the tokens will allow you to run whatever licenses you need up to the value of the tokens that you have in the pool. I'm not going to use the multi-step nonlinear here because I didn't know what everybody was running. So I wanted to make sure what I did was something that everybody could run, even with a basic license. So you could do whatever we're doing today and then try and repeat it with the multi-step nonlinear if you've got access to that license. But I haven't covered that in any of the material. We also have another solver which is called Simcenter SAMSEF, and this is another nonlinear solution that Siemens acquired, and that's something that has some very specific capabilities. So the top image you can see where you're looking at delamination of laminates. It has some quite specific modeling capabilities for laminates and progressive ply failures, some kinematic joints. It has a lot of quite specialist capabilities within SAMSEF. And again, we're not going to look at that within this session either. As I mentioned, it was 82 tokens for multi-step nonlinear. The prerequisite is that you need to have a Nastran basic license. So if you didn't have Simcenter Structures or the Engineering Desktop add-on, you would need to use 82 tokens out of your token pool. So that means you would need 164 to be able to run the multi-step nonlinear. So I just put that in there as an explanation in case you try to do something and say, oh, I don't have enough licensing and enough tokens, and that might be because you don't have the Nastran basic Simcenter Structure license as a prereq. Okay. So what are the differences between these solvers that I've mentioned? The most important or the clearest differentiator is surface to surface contact. If you have any surface to surface contact, then Sol 106, 129 doesn't have contacts. You can have node to node contact, but you can't have surface to surface. So that's a fair limitation of that solution. So as you can see in the list, 101 is what we did last week. So it doesn't handle, large displacement, material non-linearities, etc. But 106 will handle a lot of things. Obviously, that 101 won't, but contact is one that we don't have. If you have rubber material, hyperelastic materials, then we can't again apply that within 106, 129. Large strains not in 106, 129. So you've got a fair bunch of capabilities that are included in the base license, but you might need to go further. And that's where 401, 402 come in. They have the ability to do surface to surface contact. They have large deflections. They have large strains, etc. Hyperelastic materials, more exotic material models, etc. And that's what sits within 401, 402. SAMSEF is in 402, but there's also a standalone SAMSEF where you can run SAMSEF as it was as an original product. 402 is a lot of the SAMSEF capability badged into what we call Sol 402. So today we're going to focus around 106 and 129. So this is the problem we had last week. The bracket with our sort of wheel bolted into it. And last week we were well within the material parameters and the deflection was very small. So what happens if we put a much larger load onto this bracket? So suppose we wanted to put on something like 6 kilonewtons as a load onto half of our bracket. I think last week we put on something like 34.77 newtons. So, maybe 20 times what we put on last time, or 2,000 times what we put on last time. So if we calculate the stress and deflection, then we'll look at solving the nonlinear solving material and then doing the two combined. So why would we want to consider large deflection? So here, what I've done is the light gray is the undeformed shape. The red is the deformed shape. And what I've done is I've displayed it 1-to-1. So here you can see that this is the actual deflection of the bracket, not the exaggerated 10% that you would normally see as a default. So here you can see as this deforms, the load isn't only going to be vertically, it will start to have a component which is pushing towards the wall. So this direction is going to change as it deforms. So that's why I want to consider the LG disc, just to see, well, how much does the load affect the loading direction and the rotation of the bracket? And that's what we're going to consider in the first instance. So like we did last week, anything that I have in this slideshow that I'm going through with the orange background is in the separate example PDF that I gave you. I've just got it in here so you can see it in the context of what we're going through. So the first thing to do is to read in the sim file that I sent you. So again, you should be able to open that up. It was done again in an earlier version of software. So that will allow you to read it into pretty much any version that you're likely to have. So in here, notice the default is to look for parts. If I toggle it here, I can look for a sim. And when I look for the sim, I can pick up my sim geometry. So if you had the result that we finished with last week, with the mesh adjusted to give us something that was within the tolerance that we wanted to solve for, you could just extend it from that model. What I've done for this one is I just took that result and then exported it as a Nastran build data deck and then created a FEM and sim. So here we don't have any geometry underneath this FEM. So this is only mesh. Because in this part of the sessions, we're not looking to change the geometry. Therefore, I'm just working with the mesh and the boundary conditions. So underneath here, you don't have any geometry. So here we've got a FEM and a sim. But notice because I opened up the sim, it also opened up the FEM at the same time. So underneath here, you can see we've got our 3D mesh here, which we can switch on and off. We don't have any polygon bodies or anything related to geometry because in this instance, I just purely read in the Nastran input deck. So all we've got is mesh. We don't have any geometry associativity. So it's set up that way because everything we're going to do is more sort of solver based today. But if you wanted to, you could take the one we had last week and just continue to work with that. Okay. So we've read in the geometry. So now we want to go in and ultimately perform a linear analysis and see what the result is. If there's small deflections, then there's no need to run the geometry nonlinear. If the stress is well below the yield, then there's no need to run the simulation. But however, if the load in this case has gone up a long way, then this might have an effect. So when we did it originally in linear static, both of these capabilities were passed, i.e. there wasn't a large rotation, it was small deflection, the stresses were low, therefore we didn't need to run nonlinear. Now we've drastically increased the load, we do need to start and consider it. So the process that we're going to go through, first of all, you want to perform a linear analysis. You wouldn't go straight in and do a nonlinear, because if you did that, it might take you a long time to complete it because you've got to put more complexity in. You're going to have to build the model. The solution time will take longer. But then if you find you've got a safety factor of 10, then there was no real point to do the nonlinear analysis. So generally you would do a linear analysis first, look at the results, decide if you've got large deflection or high stresses above yield. If you don't, and you've got enough of a safety factor, then that's it. You don't need to do nonlinear. If you find that you do, then you would take it through, do nonlinear analysis, and then complete the process. So that's really what we want to do. So in this sim, I've got Sol 101 already defined, so you want to solve that. So in here, I've got my arm geometry with my loads. If I edit it, it's a Sol 101 linear static. So then we can solve it. And this is pretty much what we did last week. So we'll solve it linear statically. Yeah, it's just solve it over like it did last time. So like we did last time, we can double click on it and go to a result. So here we can put the deflection on. And see there, it looks a very exaggerated deflection. By default, it's going to do it at 10% of the model size. If we toggle this to be 1-to-1, then we can see what the 1-to-1 deflection is. And if we were to go into the post view on the deformation, here we can see a show and deform model. So then you can see how much that deflects relative to the original model in a scale of 1-to-1. So here you can see, this is starting to move. So the load wouldn't necessarily be purely vertical now. Okay, so we've solved it. We've got our baseline result. We can go and look at the stresses and deflections. And then we'll take it in to do nonlinear. So let me just show you that. So here we can show the deflection, like so, which is 8.7. If we go into the stress, we can put that on. So here the stresses are looking very high where we've got our attachment points. What we can do here is then go in and change the scaling to be specified. I think I set it to be something like 500. So then you can see where all of the stresses are of about 500, which if our material yield is something like 300, then we've exceeded it. So that might be something that would say that we might want to start and look at doing a material nonlinearity. But in the first instance, we're going to ignore that. So that's what we're going to do in the first section, just do a little bit of post-processing, see where we are relative to deflection and stress. So now what we want to do is go in and say, let's do a 106 nonlinear solution. So we're going to create the solution here. And then once we've created it, we're going to go in and set up some nonlinear parameters. So let me do that and explain how that works. So what I'm going to do is right click on the top, create a new solution. And so here I can just call it baseline. So this might be my baseline nonlinear solve. So it's Nastran structural. Under here, we can choose a variety of solvers. Last time we did linear static. This time we want to go down and do a 106 nonlinear. So we choose the solution that we want to run under here. We create the solution. And then when it creates the solution, like last time we went in and created some different output, we put on the strain so we could look at the error and then get it to refine the mesh. This time, because we're running a nonlinear analysis, we might want to define some nonlinear parameters. So if we come into the nonlinear parameters, here we can see how many increments we want to run. So I'm going to do 10 at 0.1. And here, what outputs do you want? If I say no, it'll just give me the output at 1 second or at the point that it can no longer do the solution. What I want to do here is get an output at every 0.1 seconds so I could either graph it to see how things might have changed, or I just want to have a smaller step to maybe make it easier to converge. But I want to see the outputs at each of these steps. So here I'm just going to say all, like so. So here, these are what we've set up. I didn't show much last time in terms of dragging and dropping, but that's the way we can do things within the user interface. So here I want to take constraints and loads and drag them into this nonlinear solution. So if we go into here, because we've created a new solution, it doesn't have any loads or anything into it. So if we expand up in here, you can see we've got a dot with nothing underneath it, i.e. it's not solid. So that means it's inactive. If I click on it with my left button and drag it, I can drag it down and then drop it. And then when I drop it, it goes to a solid circle. See, that is now active. And I can do the same with these two constraints here. So I can do a control click, drag them, and then drop them into constraints. So any constraints that I've defined previously, I can take them through and then use them in the solution. Like so. So all I've done is drag these constraints down, and now they're visible and possible to be used. And then I just simply solve it. So to solve, because this one's active, you could come up here and hit solve, or you could just right click, solve. So I think in the example, that's the way that I've done it. So here you can hit solve. It's going to do some checking if we just accept the defaults, and we'll solve it. So this time the solution will take a little bit longer, because what it's doing is it's solving at 0.1, 0.2, all the way up to 1 second. So it will take a little bit longer than it did when we just did it linear statically. We'll let it go through the process. Here you can see how it's converging, so we can look at the convergence of it. So it's gone from 0.1 all the way up to 1 second. And that's quite common in a nonlinear solve, that you see how something is converging. So here we can look to see how each time step is converging. And here we can see how that affects our nonlinear progression to a solution. Okay, so it's solved. Didn't take too long. Now we can go in and look at the result. So if I come into here, notice we've now got all our outputs. So if I look at the first deflection, it's 0.873. If I look at 10 seconds, it's 8728. So it's just 10 times what the base, what the 0.1 is. So at the moment, I'm still solving linear statically, because I haven't introduced any nonlinear geometry yet, and I haven't got nonlinear material. So the result of this nonlinear solution that I've done is giving me the same answer that I got from a Sol 101. So at the moment, my answer is identical. So here, if I go side by side and I drop on my original result and see a new plot on here, I get exactly the same deflection, but one is a nonlinear solution and the other one's a linear solution. But I haven't introduced any nonlinearities yet. Does that make sense? Everybody okay with that?
Yep.
Yeah, all I've done is chose a nonlinear solver. I just haven't introduced any nonlinearities yet. Okay. So you could have done your baseline solution of linear static. We could have done it with a 106 solver last week, and then all we would need to do is switch on the nonlinearities. Okay, so how do we introduce the nonlinearities, and how do we do that? So let's have a look at that next. Into the model. Okay. So we're displaying them at 1 second, and what you'll find is, the results are identical. So that's kind of what I was alluding to, is a linear static solution without nonlinearity is the same as a nonlinear solution without any nonlinearity. Okay, so when we perform a geometry nonlinear with the algebraic disk switch on, which is large displacement, what you'll see here is the blue line is our linear solution. So you can see we go, it's a it's a totally straight line up to 8.7, whatever it is at 1 second. When we do it with LG disp, you see that we're getting a deviation. because now that deflection is changing because the direction of the load is changing. And we're seeing a slight difference between the two. And that's what we're going to look at now. So how do we do that? Well, if we right click and clone a nonlinear baseline, then we can switch on the nonlinearities and then solve it. I've shown you in this in the images how to do that, but I'll show you in software. So here, if I right click, I can clone. That clone gives me everything that was underneath this one will be underneath this one. Any of the settings I changed on this one, such as to run it for 1 second and do 10 steps, they will be transferred because I've literally copied everything that was in here across. So now what I can do in here is call that LG disc baseline nonlinear. So I know which one it is. I think I might call something different in the example. So now if I right click, edit, I can go to bulk data, and there's a LG disp switch here that I can switch on. So if I switch on LG disp, then solve. So as you can see in here, I switch on LG disp and then solve it, and then we can look at the results like we did last time. So what you'll notice, you can see it looking to try and converge that 0.1 second step. Once it's converged it, it will then move on to 0.2. And I'll go from 0.1 to 0.2. You can see it's iterating. This time it's a little bit more onerous than it was originally, because originally the force wasn't changing direction because we hadn't switched on the LG disp. So the direction was still linear. Therefore, it was solving a bit quicker. And now it's having to look at the deformed geometry, change the direction of the load, and then see what effect that has on the solution. So it's doing a little bit more this time. And that's why it'll take a little bit longer to complete the solution. And sometimes if it doesn't converge, then it'll chop back, do it at a slightly smaller step, and then try and progress back through. So you might see it jumping backwards and forwards. There's an art to kind of converging nonlinear models and nonlinear problems that you're trying to solve. But here it is reasonably stable. It's just taking a little while. And this is one of the reasons why you wouldn't want to do this first. You'd want to start simple, do a linear static, see where you are, and then introduce more complexity, because generally more complexity means longer solution times, you need more information, it might be harder to converge, etc. And that's really, if there's a tip, don't introduce it if you don't need to. You can see again, it's still converging quite smoothly. You'd maybe use this method if you wanted to look at nonlinear buckling. So you might want to progressively step the load on and see at what point it becomes geometry nonlinear, at what point it starts to buckle. And I actually did a buckling analysis on this bracket, which I was going to include in the session, but I didn't, decided not to put it in. But you can do a linear buckling and a non-linear buckling and then compare the result. So almost there. Okay, so it's solved, and as you can tell, it took a little bit longer. So now if we go into the result and we put on our deflection, we're now getting 8.993 instead of 8.7. So we're getting a slightly larger deflection than what we had before. So there is an element of, as you change the, as you introduce a large displacement, then you do start and get a little bit larger deflection of the bracket, and the stresses are affected as a result of that. I showed a graph, so I'll explain how you can drop on a graph as well. So here, if you see a create graph, you can do it across iterations against a particular node ID. I think in my example, I've got 57970, which is at the end. If we OK that, and here we can click a new window. And what that does is it'll put in the curve of the graph, and that will then appear in here. If I go back to my baseline solution here and plot that, again, I can do a graph using the same point and then OK it. And again, here you can see what that result looks like. So we've got one and another. So if I do this one and plot, right click plot, I can plot it onto there. I can highlight this one, right click, overlay. So here I can see the difference between my linear representation, i.e. with no LG disp, and what effect the LG disp switch has on my deflection. And I can do the same thing, you know, for stresses or whatever I want, see how those things kind of vary as a function of time through the solution between a linear and a geometry nonlinear solution. So that is sort of really the geometry nonlinear side of it. Why I did it, you know, with all outputs, so I could start and do those graphs and see something meaningful as a trend. And that's why I put all of those outputs on. Here, that's basically what we got. So the next stage is to say, well, okay, let's now do a material nonlinear. So what I'm going to assume here is that I want my yield, or my yield of the material is at 300 MPa. This is the E value for my aluminium. Therefore, I can work out what strain there is at 300 MPa for the given Young's modulus. And then what I'm going to do is define a bilinear curve where I'm going to see at 500 MPa the strain is 0.05. And I'm going to define that. So what will happen is as you load it up, it'll go up to 300, then start and track along the curve to 500 MPa and beyond. By default, I think it just extends the curve at the same gradient. But you could have a real stress strain curve from test data that you've maybe captured as well. So that's what we're going to put in. So to do that, I'm going to have to go in and start and modify my material and my material definition. So I'll show you how you do that. I'm going to do it in the FEM. There are other ways and places I could do it, but I'll do it in the FEM. So to do that, notice up here, these are basically all my boundary conditions that are attached. Double click into my FEM. Underneath my FEM, I have my raw mesh, and above it, we have what we call a collector. And that collector contains information that the mesh is going to inherit because it sits underneath that collector. So if I right click, edit, it's a solid type, but it could be a solid laminate. It's whatever definition a solid could have. And then here we've got a property. I could, create a new one, copy this one and create one, or I can edit the one that's there. I'm just going to edit the one that's there. So here we're using aluminium. If I go into my library, I've got this material. So what I want to do is, I could edit it. Yeah, let's just edit it. I think in the example, I'd probably copy it. But if we edit it, what we can do is, this is just the mat 1 is just properties that we're going to use for sort of linear static. If I add on mat S1, then down here you can see we've got nonlinear behavior. So here we've got nonlinear plastic, plastic strain, nonlinear elastic. We've got different models that we can use for the nonlinear. We've got engineering, true strain, plastic strain, different ways of defining nonlinear curves. I'll just leave it as engineering, stress strain. I'm going to use a stress strain curve. And then here we can define just a table that's going to represent what we want to add in for our stress strain curve. And if we hit the equals, we can see a new field as a table. So dependent is stress in MPa. Independent is going to be strain, which we can next. It's how it interpolates. So here what we're seeing is 0 and 0. Here we want to go 1 point on our curve to the 300 MPa, which is yield. Then we want 0.05 to 500, like so. And then we can OK that. So now we've got a nonlinear material defined there. We could check it, which again, I don't do in the example, but it might be worth showing you. So here we can come into our material. We can edit it. Go down to here. And we can plot. Here's our bilinear curve that we've defined. Okay, so now when we come back into the sim, so if we look in our example, I went in, edited this material. I switched on the mat S1, activated some values, and then went down and put these values in. But here I copied it, but you could edit the one that's there. You can only edit the one that's there if it's not padlocked. It would be padlocked if it was in the library that was supplied by Siemens. If it's one that you've created yourself or has been created as a result of an import, then it will be local and it will allow you to edit it. So you might, the one we used last week was a library material, so you might find you couldn't edit it, in which case you would need to copy it. So now what we want to do is create our nonlinear material, nonlinear baseline and solve. So here we're just going to clone the nonlinear baseline and then take it and look at that. I don't want to use the one with LG disk because at the moment I don't want to include LG disk. So I'm going to take this one and clone and then call it material nonlinear or whatever you want to call it. And then again, we can go ahead and solve that. Now using the nonlinear material that we've defined on our collector in the FEM file. If you do the solution solve 401, 402, there's a MAT-NL switch that you can switch on. So you can have a non-linear curve, but if you don't put the switch on, it'll just take the first 2 points and work out the E value and apply that to it. If you switch on MAT-NL, then it will track the curve. So there's different nuances or ways that you apply it in the different solvers. So here you can see it's going through that solution like we did last time. We can see how it converges. Any questions on what I've done so far? Does that make sense?
Yeah, no, that makes sense. It's good.
Yeah.
Yeah.
Here it's saying, you know, you're outside the table, so we're interpolating. Because here we've got just very, very high stresses in certainly around the area we're fixing it. So it's just saying I had to extend the table and interpolate onto it. Again, this is an artificial example to kind of show you the effects and how you might model them. But as you can see, it just takes longer. The more, once you start and do, you know, nonlinear solutions, they can take an order of magnitude longer than just doing a linear static. So you want to be pretty certain that you need to do it before you do it. So here we're at that point. And then we start and look at the stresses, which is what we're going to do next when it solves. So now you can see on my same scale I used before, then the stress in this area is about 350, where before I've got on one of these curves. Let's see which one it was. Yeah, so before you can see it was up in the 450s, 450 plus. We're now, once we've ran it with the nonlinear material, then we're immediately, you know, getting this. So it goes all the way up to here, and after about half the load or 0.6 of the load, it starts to go nonlinear. So again, that's another thing we can learn from a nonlinear analysis. We can learn at what point does it start to become nonlinear in terms of the material model, because in this region it's still pretty linear. It's only once it gets past the 300 that we see it start to flatten off. And this will give us an idea of what factor of the load that is. So at 0.6 of the applied load is where it starts to go plastic, or starts to go material nonlinear. So it's still going. Just about finished. And here you can see, if you look at, as you can look at here, maybe initially it doesn't take that many iterations to converge, but the further you go up the curve, once it gets past 0.6, then it starts to take longer, because at this point you've got parts of the structure that are now, you know, the material is nonlinear, therefore it has to track, work out what the stresses are on the nonlinear curve for the elements, and it's starting to go through that and then achieve a convergence. So up until 0.6, it's still pretty much linear. But once we get past here, then we can start to see where we're running in a nonlinear area for the material. Something else you can kind of learn from the convergence curves. Okay, so if we now look at that result, too many here. And now we can put on our stress, limit the scale again. Like so, and then we can graph and then choose a point. Rather than choosing this point, what I could do in here is just choose wherever I want it to be. So here I can select from the model. Pick from model. So now I can pick my point here. Okay, and then draw the graph. So now you can see where it starts to track the nonlinear curve. And you could overlay the nonlinear curve to see what it looks like in terms of what you applied as a bilinear. But here you can sort of see where that goes. Here we can look at the deflection as well and see what happens to the deflection with the nonlinear material. So in here, if I now put on my deflection here, and I can see apply that result, notice it keeps this scale at 500 because that's what I told it to do in here. You can just see it to be a result. Now I'm getting 11 mil deflection. And again, when I create my graph, I can, again, pick it from the model if I want. So just pick a point towards the end. I get that graph. Can go back to my base solution without any nonlinear on it. And I've got my deflection here. So now I can overlay the two of them. So yeah, I can plot that. And then take that one there and overlay it. So now we can see. We can see what effect we get by introducing a nonlinear material on the deflection of our bracket. Cool. And then obviously the last thing that we maybe want to look at is to see, well, what happens if we run material, nonlinear and LG disp at the same time. So to do that, probably easiest to clone that one because it's already got the LG disp switch on it. So here I'll just clone it. Give it a name so I know what it is. So all included or whatever. And now I should just be able to solve that one. And this time it's going to run the LG disp and the material nonlinearity. And it'll take, again, a little bit longer. And here again, we can see the convergence. Any questions around kind of what I've done there with the different solvers, applying the material, post-processing, getting graphs? Everybody reasonably happy with that?
Yeah.
Yeah. So the fact you're scaling the load on in steps, it means you can tell, at what ratio of the load something happens in a nonlinear sense. So that'll give you an idea, well, what kind of load can I put on before these effects start to happen? So if I was to put on maybe 2 kilonewtons, then I probably wouldn't get to the point where, I had a lot of my nonlinear material or the LG disc. So if I ran it with 2 kilonewtons, maybe I could get away with doing that.
Yeah.
Yeah. So that's kind of, some of the assumptions you can draw from it. While that's running to a conclusion, I'll just finish off where we are in the PowerPoint. So, we're just going ahead and solving that. And then you get a result. So this time we're getting about 12 mil deflection. So we had something like, I think it was about 11 with the nonlinear material. And then we get a little bit more with the LG disc on top. And then here we again see what we get for our nonlinear stresses. I'll also show you some other things as well once it's solved. But what we want to do maybe here is look at the conclusions while it's going. So the conclusions that you would want to draw from the session that we've done today is always do linear statics first. It's going to be quicker. It'll allow you to make an initial assessment as to where you are in the curve in terms of relative to yield, relative to large rotations or deflections. And the results will then determine what you want to do next. Once you go in to do nonlinear, it will take longer because either it might have difficulty converging, you're introducing a lot more numerical complexity, therefore it will take longer. You need more information on the material, so you need to actually have maybe the stress strain data. You need to have it in engineering strain, or you need to convert from engineering strain to true strain. You've got to do some other work to get the information in a form that you want. Especially if you were doing it, say, with rubber hyperelastic materials, you would need to fit the test data to get the constants to then represent the appropriate model for the rubber material. So you need to put in a lot more information on a material side. And as a result of that, you might even need more analysis, because you might then start to look at a creep, or you might want to look at, what is your residual stresses after a few cycles of a particular loading. And again, all of those things might come out of the analysis that you do. So nonlinear is it allows you to understand your structure a bit more, but it might introduce more questions than answers. So then you might have to do a little bit more work to understand what is happening. So let's see where we are. We're nearly there. So we're converging relatively well. It always takes longer when you're watching it as well. Other things you can do with a nonlinear solver as well, you can do multiple steps. So you can do one step, then followed by another, followed by another. So you could do a static loading, and then you can maybe do some other loading after that and see the effect of it as a result of a process. So you can maybe unload it, and do a few cycles of that. Where we could start and do a bit more with the 401, 402, you could do bolt tightening sequences, where you could sort of decide which order you want to tighten the bolts, then go ahead and do a static analysis. Then you might want to do a dynamic analysis of that statically loaded structure. So you can do all of that with 401, 402. So you can start and look at manufacturing processes as well. So it's solved. So what I want to do now is look at the result. So notice when you got this result, you see nonlinear stresses as well, and nonlinear strains, plastic and creep. So you'll see some other outputs that you can use. So if I go into nonlinear stress, then I get some nonlinear stresses that I can display. If I go back to my original baseline, which doesn't have any nonlinearities in it. So notice in here, when we do the 106 solve, we just get normal stress. We don't get any result there that's related to the nonlinear. We don't get the nonlinear stress as an output. We only get that when we've got our material nonlinear curve and it's starting to work on that. So that's where you would start and see the values. But you wouldn't see it if you didn't have the material nonlinear. You see it because of LG DISP, but if you go into here, it just lists what the stresses are. So you can start and get an idea of where your nonlinear stresses are in your structure as well, where your plasticity is as well. So you can start and get other outputs here that might be useful to give you an idea of where the parameters are as a result of the nonlinear solution that you're running. And that was really it for nonlinear as nonlinear. Is there anything else that any questions, anything you'd like me to explain or show?
That's it. They're all non-linear experts now, Mark.
Well, you've got the data and you've seen the process that I go through. So you could vary the load. You could start and just try different loads and see what effect you have. But at least you've got some loading types where you can see what the behavior is. If you went much higher, then you'd start and see you actually see the bracket buckle. If you put a much higher load onto it, you can see the bracket literally start and buckle at a certain point. And you can do that assessment. Does anybody know how to do a linear buckling analysis? Has anybody done that before?
Yeah, I've done that one before. The onset of buckling. Yeah.
Yeah, so we could do that in here. So we could do that. We could say we want to do a 105 linear buckling, like so. And then we can take constraints like we did before. Drop them into here, and then the load. What I might want to do is copy the load, and then instead of putting in minus 6,000, if I just put in -1, then help if I drop that into the solution. So let's drop that one into here. Just drop that load in. Just the preload. It's just like that. Drop it into there. So it was letting me do some level of preload, but really where I want to put it is in there. So let's solve that and see what we get. So now it's going to go away and calculate what the linear buckling estimate is for the structure. I think I've got the result for the one I solved, so I could always show that as well, just to give you a feel for it. Here's the extracting mode. And this is the factor of the load. So here it's suggesting if you put on 37.74 kilonewtons, that's the load that it would cause it to buckle linearly. We'll see that when we get the result. Here. To save some time, what I can do is I can just go and look at results. So in here, what I've got, is the session 2 that I ran. So here I did a linear buckling. So I can open up that result. And then here we can look at the buckling deflection. But what this one does here tells you at what scaling of the load it will feel at. So here it's saying 37. I think I must have done it at 1 kilonewton rather than 1 newton. So here you can see it's 37 times my 1 kilonewton is where you would start and get linear buckling. And what I also did was I ran it non-linearly to do the same thing. So what I did is a non-linear buckling. Which I don't know exactly which one of these it was. Yeah, I don't know which one of those it is off the top of my head. But you can, what you can see from your buckling solution. So here. So this tells us how much we scale the load to get buckle, and that's the way it will buckle. It'll start to buckle along this member. So I did solve it, but I can't remember which one it would be. But let's just import one of the results and see if it is the linear buckling. Yeah, I can't find which one it was. I don't know if it was this one here. You can start and see this member actually starting and buckle if you ran it with that load. It just takes a little while to solve it, but you would see it. And you get something as a similar value where you see the buckling. So that's another thing you can extend it, so you can do a linear buckling, but then also do a large displacement buckle and see how it buckles as a result of that as well.
Yeah, so you use the linear buckle to find out what load, and then apply that to the largest displacement.
Yeah, and you can start and get, if I had the one that I've actually got, then when you look at the stresses, you can, or the displacement, you can see where it starts to sort of buckle significantly. I just can't remember what it was because it wasn't something I was going to show, so I didn't label it appropriately. So here I've got, not all of the non-linear ones that we've done, but I didn't name the one that I'd done, which is a bit awkward really, but it would be an LG disp.
Yeah.
Yeah, but I haven't got it saved. But you do literally see, that member really start and twist as a result of the loading.
Yeah.
Yeah, I think you get something like a 50 mil deflection, so the deflection is sort of very significant relative to the shape of the geometry. Okay, so I think there's a little while till the next session, Matt, isn't it? It's the middle of.
Yeah, it's a
Or the
few weeks.
beginning.
It's on our website, but we'll send out links to it.
And the next one's going to be around normal modes and vibration, I think, is the next session. But again, Matt, as he said, it's on the website and you can see the details of that one.
Yeah.
All right. So hopefully I'll try and explain what those kind of analyses are and how you might prepare to do them. If there's any questions come up, like we said last time, as a result of what we've done, by all means, get in touch. And any other questions, then, yeah, just route them to us and we'll try and answer them for you.
Okay. Thank you very much.
That was great. Cheers, Mark. Thank you.
Yeah, no problem.
Thank
Thanks,
you.
everyone.
Cheers.
Good
Bye-bye.
afternoon.
Yeah, cheers. Bye.